Hello, this is a Bullis Student Tutor, and I'm going to be talking about drag. So in physics, fluids are gases or liquids, and when we have motion through a fluid, there will be this resisting force. It's pretty much it's friction, I guess, with the fluid. It's called fluid resistance, and fluid resistance is also known as drag. So the force that is resisting the object's motion will be called drag. A common case would be if we have an object falling in the air. Air is a gas, so it is also fluid. We have an object falling down with this force due to gravity, mg. We also have a drag force, which resists its motion. And in the case of a small object with a low speed, we will find that the drag force is pretty much proportional to the velocity, and we can call this proportionality constant k. Of course, this is not always exactly the case, but if we assume that it is equal to kv, where k is some constant, then we will actually be able to determine an equation for velocity as a function of time. Okay. With that being said, it should also be noted that at higher speeds, this object, which still has mg as its force due to gravity, we also have a drag force, but this time, because it's at a higher speed, it actually ends up being proportional to the velocity squared. So this is d, it's just like k, a constant, the drag constant, and being proportional to v squared, we would end up with a different equation for velocity if we wanted to find it. We're not actually going to find an equation for the latter case, but in both I want to talk about terminal velocity. So there's a concept, and it basically states that the object falling is going to speed up and approach some terminal velocity. We denote this as vt, and this terminal velocity, once it is reached, well, it's asymptotic, so it really is never reached, but as it approaches this terminal velocity, the velocity begins to become constant, almost constant at least. And so in this case, we actually have equilibrium. We have a constant velocity. So we can find Vt using sum of force equations. So the sum of force, if we take the positive direction to be the direction of motion, which is down, mg minus kv is equal to ma, which is 0 because of equilibrium. So in this case, mg minus dv squared equal to ma, which is again 0. So we can solve, we can find that kv is mg, and thus v terminal, I forgot to write this, but we're talking about terminal velocity, and that's vt. V terminal is mg over k. In this case, we have vt squared, dvt squared, sorry, is mg, and then v terminal would be the square root of mg over d. Okay, so now we want to look at velocity as a function of time. We can actually find an expression for this. So if we take the former case again, where we had this force due to gravity mg and a drag force proportional to velocity, we will once again write the sum of force equations. We have positive as the direction of motion, mg minus kv is ma, but we do not have to assume equilibrium because this is for any general velocity. So we know that a is the derivative of velocity with respect to time. We know that mg minus kv is equal to m dv over dt. And we're going to solve a differential equation here. So one method, we can first start out by remembering vt is equal to mg over k, so that mg is actually just k v terminal. And we can substitute in, we can find k times v terminal minus v is equal to m dv over dt. So now what I'm going to do is I'm going to divide both sides by m, multiply by dt, divide by vt minus v. So what I'm doing is actually I'm just separating the variables. But I'm also going to multiply both sides by -1, and that's just going to simplify things. So I'm multiplying everything like this, v terminal minus v times dt, negative dt, over m v terminal minus v is equal to m dv over dt times the same thing, negative dt over m vt minus v. And of course I have cancel here, and I just have that negative k over m dt is equal to, I'm going to get rid of the negative just by switching the order of v and v terminal, dv over v minus v terminal. Okay, now I can integrate both sides. So if I do that, integrate, I have from 0 to time t of negative k over m dt is equal to, now the lower limit here is going to have to be the initial velocity to be consistent, but you could of course evaluate this with an initial velocity. I'm going to assume that the object starts from rest before falling, so that initial velocity is 0. So it's going to go from 0 to v of dv v minus v terminal. Okay, now I'm going to have to integrate. This first case is really easy. So all that we have is negative k over m t evaluated at time t and 0. And this next case is also quite simple. It may not look that way at first, but you actually can use reverse chain rule. The derivative of v minus v terminal, since v terminal is a constant, will just be 1. We already have 1 outside, so we can already write this as ln absolute value v minus v terminal evaluated at v and 0. So if we do this, we have negative k over mt minus negative k over m times 0, which is 0, so I won't write that out, is equal to ln absolute value v minus v terminal minus ln absolute value of 0 minus v terminal. And we can use properties of logs now. We can write this as ln v minus v terminal of v minus v terminal divided by negative v terminal is equal to negative k over mt. And then we notice that because v terminal is the maximum speed, that v must be less than v terminal. So v minus v terminal is negative, negative v terminal is negative. We actually have a positive, and we can get rid of the absolute value signs. We can just write parentheses. So I'm going to exponentiate both sides. I'm going to exponentiate so that I can cancel out this ln. And when I do this, I'm also going to switch the order of v and v terminal so that I can get rid of the negative on the denominator. And we can write this as vt minus v over vt is equal to e to the negative k over mt. And if we just did a bit more manipulation, we will come up with this. V of t is equal to v terminal. And, v terminal. We should note that v terminal is, again, equal to mg over k. So we can substitute that back in if we want, but v terminal, I think, it's nice to write out the terminal velocity in your equation. Minus e to the negative k over m t. This is the equation for velocity as a function of time. And immediately we will notice that as t approaches infinity, e to the negative k over mt is going to approach e to the negative infinity, which would be 0. So we'll have v of t, the limit as t approaches infinity, is going to be v terminal times 1 minus 0, which is v terminal. So we see that actually we get a terminal velocity as time approaches infinity. We see that we will approach a constant asymptote of terminal velocity. We can also plug in 0, time equal to 0, since we wanted the initial velocity to be 0, to be at rest. We will find that 1 minus e to the 0, e to the 0 is 1, is going to be 0, so that v of 0 is 0. So this will actually fulfill both of our requirements. We wanted that the velocity, the final velocity, will approach a constant v terminal, and we also wanted it to start from rest. And it's exponential, so the curve looks like that. This is v, this is t, and there we go. So I hope that this video was helpful, and remember that it was brought to you by a Bullis Student Tutor. Thanks for watching.